The following is a tutorial or a special presentation on a general topic of relevance to CPAC research. This tape is for the internal use of CPAC sponsors only. Use of this material is subject to the provisions of the CPAC sponsorship agreement. The following is a tutorial or a special presentation on a general topic of relevance to CPAC research. This tape is for the internal use of CPAC sponsors only. Use of this material is subject to the provisions of the CPAC sponsorship agreement.
Well, good morning. I'll give you a preliminary welcome to the meeting. And, of course, the meeting starts tomorrow morning. We'll do this all over again tomorrow at 8 o'clock. But today we'll have the workshop on chemometrics. And we have two goals. Really, this is not like an intense training course that you might get at the University of Washington, or, you know, if we go out in-house and give these courses in-house, where you have to take a lot of notes and maybe take examinations. This is more of an overview, and it's in to prepare you somewhat as much as we can for later on for the MATLAB demonstrations, because we'll be implementing a lot of the things. That's today, and then also to prepare you for the meeting. So we usually have these workshops to get people who have never been to a CPAC meeting, and they don't know any of this stuff. And of course, at the CPAC meeting, we give a little introduction, like 1 or 2 slides, introductory slides, but we try to jump immediately right into what's happened in the last 6 months. And a lot of people get lost, so we have the workshops to get them up to speed. But today it's very interesting. I see a lot of old-timers out here, so it isn't just all the new people. So it looks like some of the old-timers who have decided, say 6, 7 years ago, that they probably won't study chemometrics because it's just a flash in the pan and it'll be gone anyway. I guess they had to reconsider and come back and learn a little bit. So, welcome. So those are the two goals. And I should let you know that it's essentially impossible to train you in chemometrics. It's a huge subject. The course is currently going on at the university right now. In fact, I'm giving a midterm exam at 9:30. I won't. Of course, it'll be proctored, but the students are certainly the brightest young minds that go to graduate school at any university, as far as I can see. They're top students. We cover things very, very slowly. I mean, we're going to cover like a month of stuff here. We cover it very slowly and very carefully, and still it's difficult for them. So there's a lot. It's a mathematical subject and takes a lot of time. So in the course, we've got, let's say there's 2 kinds of people in the room. There are those kind of people who are the mathematicians, like my buddies, or my statisticians, and there is going to be some mathematics in here, so you'll have enough to keep your interest. For those of you really don't care about the mathematics so much, but you'd like to have some understanding of what these methods are doing. So when I show you all these matrices and all that business, if you start to get a little lost, because maybe it's been a year or 2 since you've had a rigorous course on linear algebra or so, don't worry about it. Make sure that I tell you what this matrix contains. This matrix contains spectral data, and this one contains concentrations, and you know, make the relationship there, and don't worry so much about the mathematical details. Or, for some of you, don't worry at all about the mathematical details. Okay. Can we turn the slide projector on? Oh, is it on? Nope. I'll go with one of my favorite slides to start with. This is an old cartoon, I think, from Scientific American or New Yorker or somewhere, I can't remember. Two guys standing out looking out the window. These are, of course, this is an old cartoon. These are computers. It says, I get depressed thinking of all the data out there, much of it yearning to be processed. This slide is actually a very important one to me because since about the mid-'60s, I've spent my entire career getting learning and studying mathematics and statistics and trying to pull as much, let's say, of those two topics into chemistry for one purpose, really, to do a better job of getting information from the data we measure in the laboratory. And then I go out to chemical companies and I'll give a talk on this subject, and all the time I have the feeling that there's reams of data, disks, all over, billions and billions of billions of numbers that they're calling information that really is data. And there's very little effort spent, really very little effort spent on getting information from that measured data. And the measured data is very expensive. So that's what we've been about. And now I see that it is slowly catching on, that people are not willing to, put that data up on a shelf and every year keep saying things like, yeah, we have a lot of data on that. We should sometimes take a look at that and maybe we'll solve the problem. That they're starting to understand that the mathematical tools are out there to take data, wring it out dry, and get rid of it. I mean, you want to store it, fine, but you'll get the information that it contains out. And that's what we're talking about here. Now, chemometrics is, focus that just a little bit. Oh, wait, maybe I could do it here. I'd rather do it here. That's about as good as it's going to get. It's a chemical discipline. It's not mathematics or statistics, but it looks like it sometimes. It's a chemical discipline that uses, develops, sometimes even creates new mathematical and statistical methods for two purposes. Let me read the first one first, because this is the one that's had all the action up until very recently, and that is just to extract maximum chemical information from chemical data. And that's very important. So exploratory data analysis, modeling, and all those types of things. We're going to mathematicians and statisticians, incidentally, two very, very different types of people, enormously different, and bringing in order to do a better job down here. But here's the first one, is really to design or select or build optimal measurement procedures and experiments or sensors or sensor arrays, or to do the design of systems, procedures, experiments better. And that's starting to take effect. And if you'll, for example, just take a look at Lloyd Burgess' talk during the meeting, you'll see that Lloyd is making heavier and heavier use of things like singular value decomposition, which is factor analysis, a type of factor analysis, to understand the instruments that he's playing with, to pull out those real small effects that normally just look like noise or give people headaches. But now we've got tools to really understand them and pull them out, separate them, get rid of them if you like. And there's a lot of that happening right now. Well, the old analytical chemist, I don't know if you could see this, from about the year 2000 BC to about 1950 AD, studied a system by just taking a sample from the system and taking it over to the laboratory and getting a datum. Like, oh, it's pH 7.2, and that's about that. That was the extent of analytical chemistry. In the 1950s, analytical chemists in particular started to use statistics to treat the uncertainty in the data, and that was a good move. But it was basically univariate statistics until, let's say, the mid-60s, or actually almost the 70s to today, where we understand that these systems are multivariate, very important word, and that a lot of things are varying, and we better start studying these in a multivariate sense, which means we get multiple, multivariate variation. We're going to get a lot of, make lots of measurements on these systems, and then use mathematics to either, for visualization or data reduction, in order to treat multivariate data. So that's your history lesson on chemometrics. And one more little slide that I always show when we start the courses at the university is that, again, we study systems. We generally take samples from the system, and there are techniques that we teach in the course that come from statistics, sampling theory, experimental design that help us do a better job here. I'm going to come back to this in just a second. And then we make measurements on these samples. The measurements aren't usually things like concentrations. Those are voltages and currents and volumes and things like this. And there's help there, instrument optimization. There's a number of things that we could use to do a better job there. And then using such topics as we'll talk about today, like calibration and signal resolution. We'll spend more of our time talking about calibration. We can get some chemical information. If we have enough information on enough samples, we can actually attain some level of knowledge of the properties of the system, and that's called exploratory data analysis. So this is what we really want. We want to get smarter about the systems that we're studying. And there are very good ways to do that. And chemometrics is involved with all kinds of tools and the development of tools to go from measurements to information to knowledge, if you will. Okay, oh, yeah, one more thing. This is actually an older slide. What CPAC is trying to do is eliminate this right here. Obviously, we don't want to take samples, but there is still a sense of sampling when an analyzer, even if it's an inline or non-invasive analyzer, when it is acquiring data, you can still think of it as analyzing samples or regions of a process or so, unless you're lucky enough to have an analytical method that can actually make measurements on the entire process at one time. It's either you've got a very, very big analytical method or you're dealing with very, very small amounts of material, either way. Okay, enough introductory stuff. Let's get going a little bit faster. Again, we'd say take a system, we take some samples on the system, and then ignore this side for the moment. This is for advanced study. We can't talk to you about this. We'll take measurements on the system, and generally the measurements are going to go into a data matrix. It's just a table of numbers for those of you who, as I said, it's been a year or so since you've had the course. We'll often consider that the rows contain all of the information on individual samples, and the columns correspond to the variables that we'll take. And we'll stick with that format throughout this short workshop. So, in other words, you might go out and take 20 polymer samples, and you measure the infrared spectrum of each of those samples. So you'll have 20 rows here, one row corresponding to each of samples. And then if your instrument digitizes, let's say, absorbances or transmission or whatever at 1,000 wavelengths, 1024 or something like, say, 1,000 wavelengths, you'd have 1,000 columns on this matrix, each one corresponding to the wavelengths associated with that position. And the numbers inside of here, the data would consist of the actual absorbances at specific wavelengths on specific samples. Got it? Now, we might have more data than this. For the first couple of minutes, we'll stick with just this. But later on, we're going to say, no, well, we might have this, but we might have some physical properties of those polymers, too, or some other chemical properties. Maybe we want to know how much it's a black cold polymer. Maybe we want to know how much one of the monomers is in there. So we might have some reference information over here. We might want to take this data and build a model to predict this other, let's say, the physical properties. We call that calibration. Other people call it modeling. It's the same idea. And you could do that for two reasons. One is to understand to get some understanding, say, what is it about this chemical measurements, the spectral data, that allows me to predict the tensile strength of a polymer, for example. Or you may not be interested in that understanding. You just may want to build these models to analyze future polymer samples that you'll see in the future in order to predict what their hardness or tensile strength or whatever is, okay? That's pretty much a good part of the course. Now, if you had only 4 samples, here's a little data matrix, these 8 numbers. If you had only 4 samples and you had only 2 measurements, you don't need this stuff we're talking about. You simply make a plot. And since the human is the best pattern recognizer by far, better than any machine, then you could see that, you make this plot. You'd plot the actual data. Now, these are the coordinates on the 2 axes. So this is measurement number 1, measurement number 2, and here's the coordinates for sample number 1. I guess, well, they're not ordered. I don't know what they are, but sample number, we could number these samples, for example, okay? But you can see right away that they're collinear. The 2 measurements vary together. When one goes up, the other one goes up. You can see they fall pretty much on a straight line. And then you could use the computer to firm this up with some statistics. You could fit the line and do all kinds of things, and if you wish, but that would be more or less univariate or bivariate statistics. Here's just another case where we have maybe 6 samples, again, and only 2 measurements, and we plot these 6 points we plot the samples as points in an n-dimensional measurement space. Here, n is what, class? What is n? 2. So it's very simple. We have a bivariate plot. There's 6 points on it. We could have numbered the points. We just left them as x's here. And you could say, hey, there's another relationship here. These 3 group down here, these 3 group up here. That may be meaningful, or it may not be meaningful. That would be your job. So we always talk about putting the chemistry into the problem, meaning what samples did you get and what are you measuring, and then taking the chemistry out of it, or the physics out of it, and that is, what does this mean that these group here? All right? The computer just works in the center, or the chemometrics, the mathematics just works in the middle of there. You have to decide what you're going to put in, and then what does it mean when you find these patterns. Well, what I want you to do now is extend this to many, many more samples. 6 is very uninteresting. And definitely many, many more variables. Well, you can see if you have 3 measurements, you can think about a 3-dimensional plot coming out of the space here. And that would be easy. There would be some 3-dimensional distribution of these points. And you can start to think about 3 dimensions and many more samples. That's fine. But when you go to 4 dimensions or higher, especially 100, or typically we work in hundreds of dimensions, you can't visualize anything anymore. You have to let the linear algebra, the tools of mathematics, work for you at that particular case. But all of the things you can do in this 2-dimensional plot, like find groupings or find straight lines or find, any kind of geometric structure, firm it up, mathematically define it, either from an exploratory sense, meaning, what is this? What's in this data? Oh, 2 groups, you see. Or from a confirmatory sense, like I want to build a model from now on that can actually separate these 2 groups and classify future points into group 1 or 2 or, beyond and much more. All of that can be done in higher dimensional space. So from now on, you will now think about at least 4 dimensions, and we'll continue with the course. All right? I would urge you to think at least 100 dimensions. For some of you who are very, very good at this in the morning, think at least 1,000 dimensions, because that's the kind of data we have. Now, I always tell my current students, they don't get this at all. I always tell my current students, the students in the 80s and the 90s students, that in the 70s, I had no trouble getting students to understand hyperspace and n dimensions. They claim they were up there all the time, see? But today, they don't understand what they're talking about. Okay, well, here's a quick example. And really, remember, all of this is tip of the iceberg stuff. I'm grabbing little examples here and there. How might we use this in an exploratory sense? Well, let's say that, in fact, this is an actual application several years ago when the health science people came over and said, well, we understand you're dealing with these multidimensional things, and we have a problem diagnosing 2 different liver disorders, and let's call it disorder A and disorder B, and we would like to see if we can help some help. Because if we misdiagnose, then the treatment we give for the wrong disease doesn't help at all, and it's a disaster. You see, the person gets very sick much faster. So we said, okay. Then I said, well, you remember doctors most of the time do univariate. So they'll look at 1 measurement, at a time, see? But their brains are more powerful than that, obviously. Some of them are. Anyway, I said, well, what are the 2 most discriminating measurements that you currently use in your diagnosis? And they said, well, pretty much the only information we get is from the enzyme concentrations that are in the blood of the patients. Liver disease, that makes sense. So I said, well, what are the 2 most discriminating measurements that you make? And these are the 2 enzymes that they said. So we simply said, okay, let's make measurement number 1 this axis, and measurement number 2 this axis. And then they took a bunch of data from patients that they knew from biopsies or whatever, they knew for sure that either had disease A or disease B, and we just plotted these patients as points in this 2-dimensional measurement space and labeled them either A or B. And now these little dots are unknowns. We don't know what they are. Well, what's your diagnosis here from this information? Not real good, is it? What you'd like to do is have some discrimination. You might say, well, there's a lot of B's over here. Yeah, but look, there's an A over here. And there's B's that blend way over here, see? Not much separation. What does this mean? In the table that you're analyzing, in the data you don't have enough information, all right? So don't beat it to death, in a sense. Don't think you're going to get it out of here, Well, there's a lot more to be said about this, but I would not want to start doing diagnosis of these 5 unknown patients here, for sure. Well, so what I told them is, do you have any more? And they said, oh, yes. In fact, the analyzer routinely gets information from 8 enzymes in the blood, concentrations. And I said, we'll make an 8-dimensional plot, and of course, then we'll analyze that. Well, they went away for about several months when they heard that. They just didn't like to hear that. But they came back afterwards. What we did is we applied a method called principal component analysis, and you'll hear about probably this afternoon about it as singular value decomposition. And I've got a slide next that shows you basically how it works, graphically how it works, and then mathematically just a couple slides. But here's what happens. The way we used it in this case is we said, all right, these points are plotted in an n-dimensional space. We would like to look at 8-dimensional space, but we cannot. Right? Oh, you might say, why don't you look at measurement number 1 versus measurement number 2? That's a plot. Then 1 versus 3, 1 versus 4, 1 versus 5, etc. Well, that's n times n minus 1 over 2, where n is equal to 8, whatever that is, 30 plots or something. But, and you might say, well, that's not too many. I'll just take time and get it, you know. But you're missing the 3 by 3 correlations or interactions, the 4 by 4, the 5 by 5. You're not seeing the result, you see. So the way we do this is we say, okay, the next best thing we might be able to do is to find a plane. A plane is a two-dimensional surface, like the plane of the board here, in the 8-dimensional space, such that, or with the mathematical constraints, that when we perpendicularly project these points, I'm going from 3 space, but you know you're in 8 right now, down to this plane, that this plane contains the maximum amount of information that we can get versus any other plane of projection. See? Got that? And the way we describe that is we want maximum variance. That's a statistical term, it's a mathematical term, so we could use that, develop the constraints. And when we do that, we essentially solve an eigenvalue, eigenvector problem. And these are these same samples projected on eigenvector 1 and eigenvector number 2. So what is this? This is the plane that I just told you about, found from the 8-dimensional space. You could think figuratively, we project the points on, rip the plane out of the 8-dimensional space, and show it to you right here. Everyone understand what I'm saying? The plane of maximum information. Now we could have taken the 3-dimensional, right, volume of maximum information, correct? That means the 3-dimensional space, such that we project, and this might be hard to think about, but project the points from the 8-dimensional space into a 3-dimensional space. That's a great reduction. You still get the maximum information. But let's do it to 2 dimensions. First of all, I'll tell you that there's 85% of the information that is contained, or variance, either it's equal in this case, that was in the 8-dimensional space, you're seeing right here. So you've only lost 15% of the variance. And I can also tell you that a lot of that 15% is measurement noise. So it's not a bad, it's an approximate look of the points in the 8 space. Got it? Now, does it look any better? Yeah, it looks a lot better. And the reason, all right, you can see you could separate the A's from the B's by just a line here. You see, unfortunately, you can't project down to the first eigenvector. You see how eigenvector number 1, if you project all these points down onto it, it's almost good enough to separate A versus B. In fact, if this ended up tilted a little bit, like a V, more of a V, boy, that would be all you need is just the coordinate, which we call the score, very important word, the score on this eigenvector, and this eigenvector we sometimes call a loading vector. You'll get more of that later on. It's all you need with the score on this axis, and you'd be able to separate A versus B. Even though I want to tell you that the computer did not have the information that these are A's and these are B's. We put that on later on when we plotted the data. But the mathematical method just said, I want to find a plane with these mathematical constraints, you know, that has maximum information. This is it. Now you might say that, okay, a couple of things on this. These are arbitrary mathematical constructs. In other words, there's nothing that says that the useful chemical information has to come out looking good this way. There are other methods that we could apply to force that issue, which means to come up with a plane of maximum discrimination called A versus B, you see? But we didn't use it here. The reason that A and B are separated is because these physicians aren't dummies. They measure things that are useful. And it just so happens that 8 measurements are better than 2 measurements. And the correlation structure, the way these 8 variables correlated, these enzyme concentrations, is represented here. And it was discriminating information. You see? So they put the right chemistry into the problem because they're making the right measurements. And 8 measurements are better than 2 in this case. Well, there's a bunch of other things to be said. We don't do diagnosis from these plots. There's a lot of other methods we use. But you can see that this point out here could more safely be thought of as a B. This one's more of an A. You notice that these 3 are right near this dividing line. And it turns out that they're University of Washington medical students who just donated blood to the study. So they're considered normal, or sort of normal, you know. Okay, medical students. Anyway, there's no doctors in here, no physicians in here, right? Good. All right. The other thing you might start to consider, you see, now you're talking about exploratory data analysis. Now we move into some hypothesis generation. You might say, I wonder if this B, or these B's over here are more ill, sicker, whatever, than these down here. Turns out, yes, that's true. you see? And you can go on from there. You can start to define a region of normality. And in a higher dimensional space, this is only 8 dimensions, but you can get a lot more clinical data. You can see as we start to feel bad or get sick, I hate to think, well, let's get off this subject. We start to move out in some axis, perhaps, that has to do with either a straight axis or a curved nonlinear axis that has something to do with a deviation from normality. Got it? Make sense? Okay. That's just to loosen you up to start. Any questions on this? Just to loosen you up to start thinking about this multidimensional stuff and that we do have methods. Yes?
You talk about dimensions, 2 dimensions, yet we don't have real problems as humans to think of 3 dimensions. Is there more information by taking this data into 3 dimensions?
Absolutely. And if you can do that, you would always do that. The more modern software that would actually go ahead and do 3 dimensions. In fact, I should tell you that this axis, number 1, contains the greatest amount of information that you can shove into one axis. Okay? So this is numero uno. You can't do any better than this. This axis is constrained to be orthogonal in that 8-dimensional space, which means at right angles, 90 degrees, or unrelated, uncorrelated, totally. And it contains the next greatest amount of variance or information that you can get from that data. And the third one, und so weiter. German, auf Deutsch. Okay? So and so. So that's exactly right. Now, of course, then you're limited. There have been data sets that we look at that we'd love to see 85% variance shoved into 2. We're the best pattern recognizers, no problem at that point. Doesn't always happen. We'll analyze some data. It's got, let's say, typically not spectral data, but more general type of data, horse race. Other types of data. You'll get maybe 11% of the variance in the first axis and 9% in the second, and you're only looking at 20%. But you're talking about hundreds of variables. So we have to go to more powerful methods that are more directed at going after what we want. Okay, moving right along. Oh, very quickly. Do you want what I just said about maximum variance? Let me just show it to you very quickly in 2 space. So I have to go back to 2-dimensional, only 2 measurements, measurement number 1 and measurement number 2, and these dots are the sample points, okay? And what this would do, what this mathematical method would do, would first translate the axis, this is called mean centering, to the center of gravity of the points. So you're going from the black axes to the blue axes now. Got it? That's called the translation of the origin. No big deal, real simple. And then it does a rotation in this space to find, this is that first eigenvector, as a matter of fact. As I said, it's a vector, but we're going to use a vector, which is an arrow in space, with its tail at the origin. We're going to use that vector as an axis. So you can now start to think of it as an axis. And it contains the greatest amount of information. You can think of, it goes through the greatest spread in the points. Does that make sense? Okay? Such that, for you statisticians, if you project these points perpendicularly onto this line and then calculate the statistic called variance on this line about the origin, it's maximum. It's the largest you can get. So there's no other axis in the space that has a greater variance or information content. The next axis, V2, this is only 2 space to 2 space, you realize. We were in a more interesting space earlier. The second one is orthogonal. It has to be 90 degrees. And it contains the next greatest amount of variance, which in this simple 2-dimensional example is the rest of the variance. Variance, change, movement. You see what I mean? That's what I'm talking about. Information, variance, change, etc. Now, probably more corresponding to Dave, if we go back and let's call this little matrix R, forget about all this other stuff up here. What we're really doing is decomposing the data matrix into some factors. Here's the matrix pictorially shown you. Here's the matrix. We would factor it into the product of 2 matrices. These are the scores. These are what's called the loadings. And we will sometimes not look at all of those axes. If we had 8-dimensional space, we could calculate 8 of these vectors. But we only looked at the first 2, you remember. Whichever ones we don't look like, that's this residual information that stays over here and out of the picture. And all right, this is a matrix that contains all of the vectors that we're going to consider. These are pairs or dyads, scores and loadings, they're called. And, all right, what else do I want to say about these? All right, these were the coordinates of the sample points on those vectors. The coordinates, what do? They position the point on the line, right? Or in that 2-dimensional graph. So the coordinates, we actually plotted the 2 vectors, the first 2 vectors from this T matrix, which is the scores matrix. This matrix is called the loadings matrix, corresponds to the measurements. It tells us what measurements are related to these vectors. Okay, now I'm not going to say much more about that, but let's just say that these numbers in this matrix describe the relationship amongst the variables. These numbers over here describe the important relationship amongst samples, or among the samples, or amongst, whatever. Chicago education, I don't know grammar very well. Got it? Okay, so this says something about samples, this says something about variables. And guess what? That's all we had, is a matrix that we had some samples and some measurements or variables made, right? So this really pulls it apart and describes it, and etc. Okay, I just wanted to bring that up to sort of loosen you up to start thinking about multivariate spaces and multidimensional spaces and that. Any questions at this point? See, now, because in class, I would probably have taken at least a week of lectures to get this far, at least. And I would have started with a short review of linear algebra. Well, all right, so chemometrics is a science that deals with lots of methods. First of all, lots of categories of methods, and within each category, lots of different methods, because there's a lot of different things we want to do with data. What we want to, and we work with most of these areas in the laboratory. What I want to do today is talk a little bit more about calibration, or modeling, if you wish, and it's going to be all multivariate, because this is a subject of a lot of interest and use. And Mary Beth Seasholtz was going to give the course for me today, and I gave her choice, either to give the course or give my exam, so she chose to give my exam, so I'm here giving the course. So she's not here today, but she is a senior level graduate student working with me. She'll graduate at the end of this year, not only with her PhD in chemistry, but her master's in mathematics. So she's been very, very helpful to have around to teach me some math. All right, so let's talk about calibration for a while, mostly using some of the linear modeling methods that can handle nonlinearities. They can, okay? The biased regression methods. Then I'm going to talk briefly about other types of architectures for modeling methods. Describe maybe the difference of going down to neural networks and things like this. And then, towards the end of the course, if we have time, I want to introduce you to the subject of standardization, or let's say how you would transfer one calibration model to another instrument, to another one, okay? So we're going to talk about some topics here, and I hope they're of interest to you. Oh, let me go back. Calibration, really relating an indirect analytical measurement to a physical or chemical property of the sample, like spectral data to physical properties or other chemical properties of interest. I mean, this is at the heart of what we want to do, it seems like, in the chemical industry. A set of calibration samples with known concentrations or other properties is used to derive the relationship for the prediction of future sample properties. So, calibration and analysis. Now, I think of that because I think more narrowly in analytical chemistry talk, you see. But I've had people from nuclear safeguards and, take this course because they didn't want to learn anything about chemical properties. They had some data and they wanted to predict something else if they could, you see. So it's much more generally, in there you don't call it calibration, you call it modeling. Well, very briefly, to dispense with univariate calibration, which means you collect one response per sample, and this would be like an ion selective electrode, or God forbid, you measure a spectrum of a molecule and you only look at the absorbance at one line. But I'm sorry, I just smashed the microphone. Examples: pH absorbance at one wavelength, ion selective electrodes, etc. Now, that's extremely limited, so we're going to dispense with that, even though that's 99% of all analytical chemistry today. Well, we'll move on to multivariate calibration, where you simply collect many responses per sample instead of one. Examples: spectroscopy, chromatography, collection of univariate sensors, arrays of sensors with scalar responses, etc., or pheograms from flow injection, or you get a lot more from doing this. Here's a problem with univariate calibration. Let's say we have absorbance versus concentration. We take our calibration samples, develop our nice calibration line, and then we analyze a sample whose true concentration is right here, except that there's some other component that also absorbs light at that wavelength that we don't know about. So we get a little higher signal. We say it's this concentration, and it's biased. It's incorrect. And the worst part is you cannot even detect the presence of an interfering component. Okay, that's the worst part. I mean, about univariate types of sensors. So either the sensors must be fully selective, as we said, not respond to anything else, or samples must be clean. And what is this? How do we get clean samples in analytical chemistry, class? Chromatography. That's why chromatography is probably the most important analytical set of analytical methods today, because we don't have selective sensors. So we have to go clean them up. How many? Are there a lot of chromatographers in the room? Oh, then I won't say anything else. Okay. What does chromatography do? It takes a big sample that we can't handle by itself and turns it into a lot of little samples that we can handle. All right? I mean, I don't want to dismiss the whole subject by just saying that. It's more than that, class. Okay. All right, let's talk about multivariate calibration. I want to talk very briefly about classical least squares. This is the fundamentals. This is what I think students should know about. Inverse least squares, the principal components regression, one slide on partial least squares. The idea here is that there is no longer any need for complete selectivity of the sensors. None of the sensors have to be selective for any of the analytes. Analytes are things that we're analyzing for. Okay, so you can have non-selective. You can do multiple analyses with the same data, analyze multiple concentrations, and very importantly, outlier detection is possible, which means you build this calibration model and you start to use it. All of a sudden, here comes a sample with something else in it, either another chemical component or an instrument artifact or something that was not represented in the calibration set. By and large, we can say, hey, this sample is an outlier. Okay, we cannot analyze. This model is inappropriate. Now you're extrapolating, and you really shouldn't do that. How do we solve this problem? I won't say any more about it except to say that you have to go into what we call second-order sensors and data, which is like your 2D methods, LC, UV, and all that stuff. And this is the subject of our very, very recent research over the last couple of years, and it's very exciting, but I won't say any more about it now. Okay, classical least squares. What do we do? And I'm going to go blast through this. You want to stop me if there's something that's confusing. And as I said, these are all matrices of data. Here's your response matrix of responses. So let's say we measure the spectra of a series of compounds. The dimensions on this matrix will be samples as the rows for our calibration samples, and the columns will be whatever the wavelengths are or whatever the sensors are. You see what I mean? And in here would be the instrument responses, absorbances or what have you. Got it? All right. Now, that's equal to, we say that's equal to for each of the samples, the true concentrations, because we're going to do calibration now, so we know what the concentrations are, times a matrix of constants plus error. And the idea is to solve for S, because we know the responses, we know the concentrations, we want to solve for this matrix S. Responses are modeled as a function of concentrations. We don't care. Statisticians care big time how you write this equation, because they say these errors have to be associated with these measurements, therefore these concentrations have no error in them. They're perfect. Well, we're chemists, we could fudge a little bit on that. Okay, now in calibration, you solve for this S matrix by inverting C, and in general, since C is not a square matrix, you just can't invert it. You use something called a generalized inverse, and this is the way it's done. This turns out to be very nice because the matrix you're inverting is usually small. It's dimensioned the number of analytes by the number of analytes, the C transpose C, okay? So that's well conditioned normally. Besides, you make up, if you can, not always, but sometimes you get a chance to make up the calibration standards. You make up the concentrations. You can vary their concentrations very differently and make this a very nice orthogonal matrix. So therefore, this step is very easy to do, mathematically conditioned, etc. Once you have S, you put it back into the equation, all right? And now what you'd like to do is measure the response of an unknown sample and predict the concentration. Well, now this is the known. This you have, S you have, now you want to predict concentration. So you solve this equation again with another generalized inverse. Now you're inverting this S matrix, which again is nice. It's number of analytes by number of analytes, real small, no problem. Usually no problem. And you solve this generalized inverse. Now you take this spectrum of the unknown sample, multiply it by this matrix, and you get the estimated concentration. Okay? All right. Now this is very nice, except there's one major hassle to the whole thing. I think it's probably on the next slide. Yeah, all right. What are the advantages? Signal averaging, because it's called one of the full spectrum methods. Believe me, you get advantages from using the full spectrum, okay, unless the sensors contain no information and just noise, and then it's ridiculous to put them in, so there's a decision there. But you get, instead of using one wavelength, you use multiple wavelengths, you get signal averaging advantage. What does that give you? Greater sensitivity, greater stability, less bias, etc. You also can obtain estimates of the pure component responses. In that particular case, that S matrix, you know what it contains? The pure chemical component spectra of those materials. So if you never had them, if you just had mixtures, you can actually calculate the pure spectra. Big disadvantage, and this is why this is not often used. It is in certain cases. I mean, in, say, a pharmaceutical analysis, if you've got a product you're going to analyze over and over and over again, and it's only 3 components. You have the pure components, you see what I mean? You could do this. You could make up your calibration samples as mixtures. You can account for any other sources of variance. So this is not a bad method to use. There's just a major limitation, is that you need the calibration information about all of the chemical components that contribute to the response. Oh, see? Because when you're modeling the responses, everything over here that's non-random in here has to be accounted for in here. So as you develop your calibration set and you measure your spectra, you have to know the concentrations of all of the components. That's very limiting. We don't always have that, so what we're going to do is we're going to jump over to what's called inverse calibration model and get around that. The other thing is, what if I'm not interested in concentrations? What if I'm interested in octane number of gasoline? Well, this is impossible then. You can't even use this method at all. It doesn't make any sense, you see. But just to understand that when you write the equation this way, you have to account for all non-random variance on the left-hand side, and that's very restrictive. This has to be only random. Okay? Not a bad method, just highly restrictive. All right, so what do? Is we jump over to something called inverse least squares. And what does that mean? Just turn the equation around the other way. C is equal to R times B. Now, I just put C and R on the different sides of the equation, if you'll notice that. Before, C was a matrix. Allow me to go to a vector now, so which means we're only going to be concerned about predicting the concentration of one of the components in the sample. That's actually its biggest advantage, to turn this equation around. So this would be a vector of the known concentrations of that particular analyte in those calibration samples, right? Maybe 20 calibration samples, or 10, or 50, or 100, or whatever, but you know the concentration. Or physical property, or anything else you want to predict. So this is much more generally useful. This matrix is still R. It contains the spectral data responses, or the other measurements that you're trying to predict from. This is a little vector now. This is remember the S vector was the unknowns, constants that we wanted. Now all we need is a vector of them, so we want to solve for B. And here's our error that says that the error is here. Now, the concentrations are modeled as a function of the responses. So therefore, 2 things. All we have to do, what this B does, is it picks off the information in R that relates to C. And the rest of it is just orthogonal. It's dumped aside. The other thing is that, but the statistician now stands up and says, but the only error has to be in these data right here. These data have to be perfect. And we tell them, as analytical chemists, they are. There's no error in my measurements, right? Analytical chemists get very upset when you start to, tell them that there's uncertainty in what they're doing. All right, in any case, so statistically, this is not well-founded, understand, because the error should be here when you're solving this equation, but it's the way to go because, as you'll see. Now, okay, now what do? In order to solve for B in a least square sense to minimize this error, and assuming this is the correct model, we simply invert R, bring it over on the other side of the equation, and that's written here by a generalized inverse. Since we know R and we know C, we can solve for B. That's the estimate. Having this vector here, what do we do for prediction? We simply measure the spectrum of the unknown. That's R, vector R. Multiply times B. We get a single number out. That's the concentration, estimated concentration on the unknown. So calibration, analysis. Real simple. The problem is finding the inverse of R, because the dimension of R transpose R, which we must invert, is equal, the dimension is the number of variables or sensors, let's say, by sensors. So if you have infrared spectrum, for example, you have, it's 1,000 by 1,000, it's undoubtedly what we would call singular, and this does not exist. So crisscross, you can't do this. All right, so you lose the advantage. What do people do? They say, well, we have to throw away sensors till we get down to the point where this matrix is invertible at a full rank. So they use techniques that you probably have heard of called stepwise regression. All right? So we start throwing away sensors. Actually, what we do is we try to grab the best couple of sensors until we can't invert this anymore, take a step back, invert this, and then solve and go on from there. But we have to throw away a lot of data. Now, the analytical chemist doesn't mind you doing that, actually, but I do. So the idea is the problem is to find the inverse of R transpose R. To calculate the inverse, a matrix must be square. It is. And full rank, it generally isn't. Because we usually want to make many, many more measurements than we have to get this signal averaging advantage, etc. So this talks about what is the rank of the matrix. We don't have time to go into that. So what do? We select a few of the responses so that's equal to the rank of this matrix R, which means we throw away a lot of data that we paid for. Don't like that. So now what about inverse advantage, inverse least squares? The advantage is we need the calibration only for the components we're interested, the one component or multiple components that we're interested in. Okay? That's a big, big advantage in a practical sense. See, that allows us to, and even if you're not interested in concentrations, as I said, you're just interested in octane number, all you do is put the octane numbers in that C matrix and go ahead and try to build your model to see if the information's there, or physical properties. You don't have to account for all of the variance in the spectra. Huge advantage. This makes this practical. This is a practical method. The disadvantage is the method cannot take advantage of the many sensors, so you don't get any signal averaging at all. Well, obviously this is solvable, or else I wouldn't be up here. And there's a couple of methods that are very popular. One's called principal components regression, the other one partial least squares. They both solve this problem very nicely. These are methods that are often called linear modeling methods because they take linear combinations of the original variables to make pseudo-variables or surrogate variables, and then you play with those. You'll read in the literature that they don't handle nonlinearities. That is not true. They certainly do handle nonlinearities, but certain types of nonlinearities they do not handle efficiently. Right? They don't handle them efficiently. We'll talk a little bit about this as we move along. Okay. So how does it work? Well, number one, let's talk about principal components regression. It's a method that I better not talk about it. It's been around a long time. Statisticians, this is not a secret to statisticians. The chemists, it was a secret, embarrassingly so. Oh, incidentally, there's the classical and the inverse method. You'll read in the literature about the K matrix and the P matrix. That's chemistry inventing the wheel again. Okay, the statisticians knew about classical and inverse regression many, many years before the chemist invented the K matrix and the P matrix method. So you're getting the straight skinny here. All right. So first of all, these methods are biased calibration methods because some of the data is discarded. Now, I don't necessarily mean we're going to throw data from some of the sensors away, but we're not going to include all the information or variation or variance. We will discard some, hopefully that which is noise related, just the noise. So there's a little filtering that's done. But if you're filtering anything, that means you're not using all of the data. Therefore, you don't have what's called the least squares solution. You have what's called a biased solution. Now, biased normally means bad in human talk, but it is not bad in this case. It is usually good. All right. So, turns out, what's the model? Here's the model. It's just what we just talked about. We use the inverse calibration model. We're going to put concentrations on the left, or whatever you're trying to predict, property you're trying to predict on the left, and the measured responses on the right-hand side. And the idea is to solve for this B again. And to write it more simply, we'll solve it this way. We'll bring R, multiply both sides on the left-hand side by something called R plus, which is a pseudo-inverse. And you'll probably do a lot of that this afternoon or around lunchtime. Instead of eating, you'll do this on the computer. Where R is a pseudo-inverse of the response space. And if we can calculate this R plus, all we have to do is, so we have the responses, we calculate this R plus, and multiply it by the known concentrations, that gives us B. And how do we do analysis or prediction for future samples? We take this B, same as we did before for inverse. multiply the unknown spectrum or the unknown measured data times this regression vector, and you get the concentration estimates. So the only difference here is how we calculate this R+. Now, we have published work in the literature in the past that shows that all of the methods that you'll hear about, latent roots regression and principal components regression, PLS, are all different ways to calculate R+, to invert this matrix, with slightly different variations that are positive or good or bad, okay? Okay, that's it. I think what I do, and all right, again, in an effort to move towards what you're going to be doing on the computer, the way we do this today, if we're going to do principal components regression, is before we do R+, we have to factor R. So now we use the singular value decomposition, just an algorithm that breaks the matrix R into the product of three matrices, U, S, and V transpose. Sometimes S is written as capital sigma in the literature. Where U, S, and V have very special properties. All right? And U and V have orthonormal columns, which means their column vectors, one and are orthogonal or unrelated or at 90 degrees to one another. Okay? U describes the information in the sample space. V describes the information in the variable space. Remember what I was saying about factor analysis? It's the same thing. Okay? And S is a diagonal matrix. Now, as I said, the columns of V explain how the original responses contribute to the new set of coordinates. Let's just say how the variables are related. The columns of U explain how the samples vary on these new axes. Those are the so-called related to the scores. The elements on the diagonal of S show the relative importance of each of these pairs, which means you got a U vector and a V vector. They're a pair, and you want to know how important they are or what their magnitude is, and those are the singular values. Now, if you know about factor analysis, and you're an expert because I just trained you on this stuff. You break it up into scores and loadings pairs. Remember, we took a matrix, we decomposed it into the product of two matrices. The eigenvectors, those are the V's, exactly the same as here. And the scores that we plotted, like the coordinates of those people on the clinical axes, that would be equal to the matrix U times S. The scores are U times S. So singular value decomposition is related directly to factor analysis, and in fact that's one of the questions on the examination today, but you can't do anything with that because by the time you get to a phone, it'll be too late to contact any of the students. Make any money doing it. So what does this amount to? Back off a little bit to saying we need to invert R+. We saw that from the last slide. The way we're going to do it is a very, very slick way to do that is we're going to first do something called singular value decomposition, U, S, V transpose. Then we're going to operate on U, S, and V transpose. We need the pseudo-inverse is approximated by R+ is approximately equal to, this is biased, that's what we call biased regression because it's approximately equal to, V bar, S bar, inverse, U bar, transpose. Now what is this stuff? Well, what we do is we do this decomposition. And remember in the factor analysis thing I talked to you about, principal component analysis, I told you that we only looked at the first two vectors in the clinical data case, right? But we could have calculated 6. Is that correct? I mean 8, total of 8. But we only looked at the first two. The way we do this is that we do the same thing, but we use a method called cross-validation, which I don't have time to discuss to tell you about, that tells us how many of those factors contain non-random variation. Okay? How many of them contain good variation or non-random variation? So the first one generally does, the second one, third, fourth, fifth, but then you get down to some level where beyond which all of the variation in those vectors is random, which means if you make these plots, like the clinical plot, one versus another one, it just looks like a shotgun test pattern, just random noise, you see? So what you do is you keep only those factors, those vector pairs, score loading pairs, this is a little tricky, but we'll get off this in just a second, that contain non-random variation. You keep those in the matrices U, S, and V. You throw away the other ones. So that's why we put bars on top of these, because they're not the actual full matrices. We truncate. We get rid of the random variation in those vectors, okay? Number one, so U, S, and V transpose are truncated. Now, how do we do the inverse? This is beautiful. You have to watch this. We had USV trans. We take the V that was on the right-hand side of the equation, called the right singular vectors, transpose it, put it on the left, put it over here. That's pretty easy. You just tip a matrix on its side effectively to transpose it. That's no problem. You take the U matrix, which was on the left-hand side, transpose it, put it on the right-hand side over here. I mean, that's trivial. No problem there. And the only thing you have to invert is this little S matrix, which is very small, square, and has numbers only on the main diagonal, zeros everywhere else. Well, in case you don't, if you've forgotten how to invert a matrix that's a diagonal matrix, you just take the reciprocals of those terms on the diagonal, 1 over those numbers, and that's it. Which, you see what I mean? That's the only mathematical operation you do after singular value decomposition. There it is. So where some of the factors have been deleted. And the deleted factors mostly describe the random noise in the measurements. So you've done some noise filtering, and then you have a very, very clean way to do this. I'm just going to take a couple more slides, and we're going to take a break. Another minute or so. All right, there's another. You notice that this singular value decomposition, or this data reduction, was done only using the response matrix R. It was ignorant of the fact that what it was trying to do was related to the matrix C, or the vector C. Hey, you know what I mean? All partial least squares does is it does the same type of decomposition, but it takes some advantage of knowing that what we're going to use this decomposition for later on is to relate it to C. So it brings in the information from the known concentrations in doing this. It's about as much time as we have to spend. So the response matrix is decomposed and truncated as in principal components regression that we just described in detail. But the decomposition is calculated using the concentration information as well. And I think this is going to be real good. Let me just stop right there and say, all right, so what have we done? We've talked a little bit about how the multivariate space. We've got some tools that we can play in this, lots more than we're going to have a chance to talk about today. We said, let's talk about the subject of calibration, which is just modeling. I measured something and I want to build a model so I can predict something in the future or understand the relationship between what I'm measuring and what I'd like to know. And we've talked about the classical way to do that. We saw there was a problem with that, so we flipped it over. We had to know too much, so we flipped the matrix over, flipped the problem around. We did the inverse. We said, oh, there's a problem computing that. We have to throw sensors away. We don't want to do that. So we said, we've got these biased regression methods called PLS, PCR, and that we've done a lot of work in the past with these methods, and that's where we are right now. Okay? So we'll take about a 10-minute break. I've got 9 on the button. I don't know what you have, but I got 9 on the button. At 10 minutes after 9, I'm going to start talking. I may be talking to myself, but I'll start talking, and we'll talk more about some of the more recent things and have a good coffee break. Okay, well, partial least squares is a method that was one of the earlier CPAC technologies that was transferred 5 years ago or so. And today there's been a lot more interest in some of the methods that, let's say, model or handle nonlinearities in the data more efficiently than PLS. But I have to tell you that we get excellent results from using partial least squares, or usually partial least squares will work as well or better than principal components regression. And that is, when the decomposition is done, it's using the concentration information, so it has a tendency to pull in less variance into the model that's not related to what you're interested in. Now, we know about the theoretical relationship of PLS. I mean, it was used for years in the chemometrics community as an algorithm, and the statisticians ignored it because they are interested in mathematical methods, not algorithms. You see, how do you study an algorithm? But we now know theoretically everything about it. We know that PLS and PCR are methods on a continuum of an infinite number of different methods, etc. And in fact, those methods that model with C is equal to R times B, we have a method called parsimonious regression that will give you the best model in any case. In other words, you won't be able to do any better than that with that type of model. So what I want to do, so there's been a lot more work done, and I won't say much more about that. I know that you each have at least one, hopefully more, chemometricians in your companies. That only makes sense. So you'll have to get them working on some of these other methods. Good. Now I want to tell you, just give you one slide. We spent a lot of time also talking about diagnostics. You can build these models, but then what? And I'll just spend a couple slides. We'll talk about one application and clean that up and get on with some of the other things. One of the things that we've talked about is when you're done with building your model, and this is only one of many again, we're jumping across these icebergs again, there's a plot that we like to look at, and it's called leverage versus the studentized residuals or errors. This is just a plot of statistics. And these samples would be our calibration samples plotted in this plot. And you could put unknowns in this as well if you'd like. But what this says is since we know the concentrations, we can, of the calibration samples, we can build a model and then run those samples through the model to see how well the calibration model is doing on those samples. You see what I mean? In predicting their concentrations, considering them for the moment as unknowns, you see. And then we get the predicted concentration and we know the real concentration, we can compare that. Well, a couple of other steps, we have to weight it certain ways, and I'm not going to go into that, but we studentize this and we leverage correct these residuals, and that's plotted on this axis. And sometimes 0 is in the middle here because we're interested to know, did we guess the concentration too low or too high or so, but here we're just looking at the absolute deviations from the true. Now we'd like to see all of them at 0 here, but obviously the model isn't perfect, so it doesn't predict all of the concentrations perfectly. All right, on this axis, we have what's called the leverage. The leverage is a statistic that tells us how influential that particular calibration sample was in determining the model. If that sample is a very, very average sample, near, back to your n-dimensional thinking of the samples in a measurement space, if that sample is somewhere in the middle of the data set, it's not going to have much leverage, you see, in defining the calibration model. Now, the model isn't a line, you realize. It's a more complicated structure than that. If it's out at the end somehow, it's going to have a high leverage value. Now, it can be out at the end or be unique type of sample for at least two reasons. One is because it's maybe just the lowest concentration one you have, and it should be out there, you see, or the highest concentration or something like that. Or it might be improperly measured. It could be unusual because it's been poorly measured. You see what I mean? The spectrum's in error or something. So, how do we interpret this whole thing? Let's look at the four extremes, the four corners of this plot. When I find a sample down in the lower left-hand corner, I say, no problem. It has a low leverage, which means the spectrum is not very unusual. It's probably okay. Remember, statistics doesn't prove anything, so I'm saying it's probably all right. And the model is not having any trouble predicting its concentration. No problem down here. This is probably a good sample. I'd like to see all of them down in this lower left-hand corner. Move up over here. This sample has a high leverage, so it's an unusual sample. This guy over here. But the error is low, so the model's not having any trouble with that sample. You see what I mean? It's accommodating it quite nicely. So I would still check the spectrum on this one, or the measured data on this one, for two reasons. First of all, anytime it's high leverage, it could be that it's an outlier. But also, even if it isn't, if the spectrum was measured perfectly or the measured data was perfect, excellent, it has a high influence on building that model. So you want to make sure that it was done right. You double check these guys at the high leverage. Understand? Okay. Now, let's look at this extreme over here. Here's a sample that has a very low leverage. The spectrum is quite normal. It's just like a lot of other ones in the data set. But the model is having one heck of a time. It just cannot predict this concentration very well. That leads me to go check the reference concentration on this one. You see what I mean? Maybe this is octane number in gasoline. I would send that sample back to the octane engine to make sure that that was measured correctly. Because the spectrum is not unusual, but the model's having a terrible time coming up with its concentration or its property. See what I'm saying? So this would lead you first to check that reference value for that one. It doesn't mean that the spectrum can't be bad. It could be bad. It's just that it's not unusual. It's a very usual one. So that's what I would check first, and if that checked out, I would go ahead and check the spectrum anyway, anytime they're out this range. Here's one that is high probability of being an outlier, class. I mean, the spectrum's highly unusual, and the model's having a heck of a time. It can't accommodate it. You know what I mean? It's not fitting it very well. And usually when you see a point out here, it usually takes one of its own principal components just to model that one single point. So that's highly probable as an outlier. If it isn't an outlier, let's say you check the reference value and you check the spectrum, it's fine, checks out. You know what? You know what that says? Bad experimental design. You either need to take this sample out and deal with that class of material separately, or you better go get some more samples that look like this one here and beef up that part of the calibration set. Okay? So we've spent a lot of time, and there's lots of CPAC publications on diagnostics, etc. So we don't, you know, come up with nothing out of these things. Well, I'll take an application very, very quickly. It's one of the first ones. Jim Callis, who's also a co-director at CPAC in near-infrared, some years ago had the idea to take near-infrared data and relate it to octane number, and of course that's of high interest to the companies today. He went to California, could get some gasoline samples. California is a state that measures its own octane number, so they had a laboratory to do this. And he got, in this particular case, let's just take a look at unleaded gasoline. He had 43 samples of unleaded gasoline where the octane, let's concentrate on the motor octane number, ran from about 82 to 87.3 octane number. So he then used principal, here are the near-infrared spectra. Now this is channel number. This is a 700-dimensional space. There are 700 digitized wavelengths along this axis. The data runs from 650 nanometers to 1235 nanometers. 1235? Okay. And you see that this is all 43 spectra plotted on top of one another. If you're not into near infrared, you don't know anything about it. Normally, this is why near infrared was never used, because you know here you got 43 your samples and the highest to lowest octane number, and heck, there's hardly any variation there. You know, so that's why people said, oh, it's useless. Also, it has low extinction coefficients. Well, that's an advantage because you can look at thicker samples. And what else? The other thing, little philosophy here for you analytical chemists. This kills me. We've been so biased to think that resolution is important, and resolution exists only on this axis. We know what spectral resolution is, right? And this is low resolution. You'd go up into the second overtone bands or up into the mid-IR to get higher resolution, right? Well, come on, class, that's crazy. There's another axis we're talking about here. There's resolution in this axis as well. We call it signal to noise. And in this region of the electromagnetic energy spectrum, the instruments that we have signal and noise as what? 10,000 to 1 or 100,000 to 1, which means extremely small shifts in these little intensity values on this axis are highly meaningful. Understand? And while we don't like to see that, because we like to see lots of sharp peaks, because we think resolution exists only on this energy axis, that's not true. These multivariate methods take it wherever they get it, on the intensity or the wavelength. If you want to see more, you can take the derivatives of these things. Is this first or second derivative? I think it's first derivative. Yeah. And you can see that there are large changes, and these changes are in the methylene stretch and the methyl stretch and the aromatic stretch, etc. All right. Well, what you do now with principal components analysis is you start pulling out these factors and use a method called cross-validation. How does that work? Briefly. It took me about an hour and a half to describe this, but that's with my students. I'm sure you'll get it faster. You take some of the data out of the calibration set, you build a model, and you see how well it predicts the data left out. Put that data back in, take some more data out, do it again, you see. Back and forth, and you only look at how it's predicting. You don't care how it fits the data. We don't care how a model fits the data used to build a calibration set, except for outlier detection. We care how predictive it is. So you keep doing this till each sample is left out once and only once, and that's called cross-validation. Now, each time you build a model, You could use 1 factor, 2 factors, 3 factors. These are the principal component things we were talking about earlier briefly. And as it is, as you start putting these factors in, never mind these little up glitches, that's real life. You continue this, and you're looking at the standard error of prediction as a function of a number of factors. And pretty soon you'll bottom out. And at this point, it was 7 factors. And this says you have to use a 7-factor model. It's highly nonlinear, relating near-infrared spectra to octane numbers should be nonlinear, unless we're real lucky. Use a 7-factor model out here, or 6, I don't remember what he used, to build the calibration model. So this is how we pick the number of factors. With that, he was able to do the standard error estimate of prediction to 0.39 octane number, and I'm told octane numbers are good to about 0.3 of an octane number. So you see, you're building a model based on near-infrared to predict octane to about 0.4 of an octane number. I'm also told you could do better than this, but you realize you can never do better than your reference number. So if your octane engine is your reference and it's good to 0.3, you could, even if your spectroscopy is a lot better than that, which I think most people, spectroscopists in the oil industry, are telling me it certainly is, how can you prove it? Because your reference values are the defining limit. Good problem. Okay. Now, what else can we plot there? I'm just going quickly through this. There's a lot more scores and loadings plots we could look at. Here are the true values of octane plotted versus the fitting numbers, and you can see that they lie on roughly a straight line. So it's 0.4 of an octane number, a standard deviation. You notice sample number 21 here sits off the line, so which means its true value is right here, and it's predicting a much higher value for octane number, etc. And there's some other ones, 40, 26 are at the ends here. So when we look at that leverage corrected residuals versus leverage plot, this is what it looks like. Now I know that here's 0 at this particular case, so this is predicting too high and predicting too low. You'll notice that, and here's the leverage value. Here's that sample number 26. Where is it? Let me go back here. 26. Here's sample 26 and 21. Okay? You'll notice sample number 26 has a very, very high leverage value. So it's an very unusual spectrum. But here's 0 error. It's not having any trouble with that whatsoever. It turns out we checked this, and there's really nothing wrong with this. So this says this is a type of gasoline that is not very much like the other ones. So we have a better experimental design is needed here, right? We need to get more samples that look like sample number 26 to incorporate in the model. Sample number 21 is way down here, and that says it's an extremely low leverage sample, but the octane number is way, way down here. You see, it's predicted, it's way off. The model just can't incorporate that. When we send this back to the octane engine, this value was incorrect. So it was measured incorrectly as a reference. The spectrum's fine, the reference value's off, etc. So that was just any questions on that? That was just a quick application of take you through it. Okay, I forgot I even had these slides in here. Well, let me jump ahead a couple of slides here. One of the things we spent a lot of time on in these references in the Journal of Chemometrics with Abraham Lohrback is working on the uncertainties of predicted values. Now, this was an unsolved problem in the field of statistics, but what it meant was we predict an octane number or we predict a concentration with one of these multivariate models. Well, what are the confidence limits on that concentration? And the problem was it was very complicated because the uncertainties came from the errors in the, let's say, spectral data in the calibration set, the errors in the reference data, and the errors in the unknown spectrum. And these 3 types of errors propagated in a very nonlinear way to give you these errors in what we really wanted in the concentration. So we have some of this. It's been pretty much ignored out there in the world, but it's in the CPAC PLS program if you ever wanted to use it. It turns out people don't like to report confidence levels too much, I think. All right, that was where I was going to break, so let me continue now. I want to spend time on 2 more topics. 1, nonlinear types of data, and 2, and just briefly let you know what's going on here, and then 2, standardization, if we can get to it, which is a fun topic. You'll hear lots about nonlinear types of data analysis at the meeting. I guess on Wednesday is our time. Yeah, Wednesday I think is when we're on. And you'll also hear Youngdong Wang talk about standardization. So those are the topics that are, going to be presented this time. Well, what do I mean by nonlinear? let's say our calibration data, and you're in higher dimensional space right now. You're up there in some 1,000-dimensional space. Let's say our calibration data fell on a line, but the line was curved in some strange way. Well, what is the dimensionality of this line? The dimensionality is 1. It's single dimension, but it's nonlinear. One-dimensional, but nonlinear, see? Now, how can principal components analysis or any of these linear modeling methods model this data? They need 2 components to do it. You see what I mean? This curve happens to fall in a plane, and a plane is defined by 2 factors. So if you had data like this, and you use these principal components regression or PLS, and you wanted to incorporate this data, it would force you to use 2 factors, when in reality the data structure is 1, but it's nonlinear. You see what I mean? When you model a nonlinearity, you're going to take more factors than is intrinsically present in the data, because the data is going to curve. Well, okay, let me stop right there. So these methods that we talk about, and we're under intense study in collaboration with people in chemical engineering, Brad Holt and Sam Lee, who will also talk, people at the University of Tennessee, and our TIE grant, NSF TIE grant with another center, and actually more people than that, people at like Jerome Friedman at Stanford University in statistics. You'll hear a lot about that, and there's more poster sessions about nonlinear methods coming at it from all different approaches. Now, one way to handle it is to say, well, this is just an artist's representation, it's not real data. Let's say the relationship might be nonlinear, but in local regions, it's linear. So you could use a piecewise linear type of approximation. What that means is we could use a method called locally weighted regression, and we have papers, and we've used this method quite a lot, and we've used it. It's a very excellent method. It works rather well. And what it says is, if I want to predict, the open circles are that's my calibration set of samples. Okay. If I want to predict the concentration or some property of this particular sample right here, you see this is an unknown, this dot. I don't attempt to model use all of this data. Rather, I use a local region. I throw out all of these samples, and use this region right here, or a smaller number of samples in the local weighted area to build my model. You're building a separate calibration model for every sample. But with today's computers, that's a piece of cake. It's no problem to do that. So for this sample, you'd use an entirely different set. Okay? So this would be more consistent with a company having a large set of historical samples for a long time, and using just those particular samples that are most relevant to the particular sample that you're analyzing at that particular time. Now you can use what I just said, you throw away these samples, that's a drastic weighting. The weightings are either large numbers or 0. You multiply by 0, that sample's out of there. Or else you could use a weighting that diminishes the influence of the samples as they proceed away from that sample. Okay? Now the nice thing about this is you're still using these linear and biased linear modeling methods, which have all these nice diagnostics, and most of these other methods do not have them. As we move away from this, we get back to having a calibration model, but no diagnostics, no statistics, no uncertainty propagation, no nothing, you see? So this is one way to go. Here's another way, nonlinear principal components regression, and there's been some papers, we've worked on this thing, and Tormod Nays in Norway, who was at our lab for a while, he's worked on this quite a bit. And that is when you take these score values, instead of just fitting the scores to the concentrations as surrogate variables, you can fit cross terms and squared terms, and you can make these score values nonlinear and then do your least squares regression at that particular case. Another one, I'm just jumping over the tops of these, is if you follow the mathematics of PLS, it's like 2-factor analysis. You decompose the R matrix, then you decompose the concentration vector or matrix, then you relate the 2 decompositions together. And while you're doing that, you can relate them in a linear way, or you can use a nonlinear way too. So you can bend the 2 methods that I talked about, principal components regression and partial least squares, you can bend them to be nonlinear methods as well if you wish. All right, so, and there's a lot of work that's been done on this one as well. Now you're probably starting to say, are there more methods? Lots more, coming at it from all points of view. Are they understudy? I think just about everyone I've ever heard of is understudy at CPAC at the moment in these big studies. And more than just studying how well they work on data, we're really understanding mathematically how they work. then the next question is starting to come to your mind. I can already see it. Is like, well, which one's the best? At this point, none of them are the best. They all work differently in different situations with different types of data. So now we're talking about an active research area where the answers are not clear-cut. A couple of slides here. As I already said this, we're not interested in how well the model fits the data. Of course, we want a good fit to the calibration data. We're more interested in how well the model predicts, okay? And the way we determine that is by measuring something called the standard error of prediction. And it's determined by cross-validation, and that is you take some of the samples out. Usually leave one out, cross-validation. Take one sample out, build a model with that one sample left out, then use it to predict its value for that one. Put that sample back in, take it out, build a model over again, and do that. If you have 20 samples, you do that 20 times. And then you compare the known concentrations for those samples when they were left out of the model building phase with the model's predicted samples, divide the sum of the squares by the number of total samples, and that's called standard error prediction. There's some assumptions here that says when you're all finished, of course, you take all of the data, dump it in, and build your model. Use all of the data. And you're assuming that that model that you build with all of the data is the same as the models you build when you pull only one sample out. And you can see that if one sample was a strange one with a high leverage or an outlier sample or a very unusual one, that would not be the case. But that's still what it is. The point here is that we're interested in predictive ability of the models, not just how they fit. Okay, now I want to talk to you. There's two more topics. One is what I call architecture of the calibration method. Now, all of these methods are mathematical, and they might have some statistical trappings around. In other words, how does the error get shuffled through and all that business. But they're mathematical models. Anything that you want to predict from anything that you can measure has some underlying, quote, true mathematical function that describes what you're measuring and how it relates to what you're trying to predict. In most cases, that underlying relationship is unknown and will probably remain unknown for our lifetimes. But there's some function there, that's true. All of these other methods, PLS or nonlinear PLS, are all trying to represent that function to the best of their ability within the way they were programmed, what I call their architecture. And that's what I want to describe to you, because in understanding what the heck is neural networks and all that stuff, how does it relate to this or that, the best way I found to talk to students about it, at least the initial discussions, are based on how the data flows through the mathematics or through the model. Can we do that? You get what I'm saying? All right. With inverse least squares, it's the simplest type of situation. And this is meant to mean a vector of data, like a spectrum, okay, a spectrum, which means there's a bunch of numbers in this vector, and it's, the absorbance is measured at a variety of wavelengths. What happens? They get multiplied by the individual regression coefficient vectors, and this is just a dot product of, or this is shown algebraically, and this is the way it's shown linear algebraically. It's just a dot product of two vectors. You sum the squares of the products of the individual components, you end up with a sum. That's the predicted value here. It's not marked as concentration set. It's y, but don't let that fool you. This is your estimated property, okay? So you see the architecture is very simple. It just all gets multiplied down into one number. Got it? So it flows down very simply. Okay. And therefore, you can only, this is very, very linear types of modeling. Okay. Let's move up a little bit. What do we do when we use one of the biased regression methods like PLS or PCR or some of the other ones, latent Ritz regression and you name it? Well, we calculate these factors that I'm talking about, these principal components, let's say, or PLS loadings, vectors, or whatever the heck you call them. It doesn't matter. But you calculate these little variables, and these are surrogate variables that you're going to use as if they were measured. And how are they calculated? From your original data. It's linear combinations of your original data. So you take your original vector, and you use the weights, the loadings vectors, to calculate the first score for each of the samples. Then you might, depending upon how many factors you look at, remember in clinical we looked at the 1 versus 2, but normally when you build these models you use more. You might use 3, or this could be 4, 5, 6, 7, 8. Then the second step is to relate these surrogate variables, surrogates, to what you're trying to predict. Okay? Now the interesting thing here is, of course, we're going to truncate. We're not going to use all the ones we can. We'll cut it off down here at the bottom. But the interesting thing to note is say, wait a second now. Kowalski tells me that these are linear combinations of these, and this is the linear combinations of this. So they're all linear combinations of everything else. That means, and it's true, that we should be able to reduce this back to one single linear combination of the original variables. And that's indeed true. That when we're all done calculating all these surrogate variables and we use them to truncate and we flop, and we're really separating the signal from the noise, if you will. When we're all done, we can go back to the same old model, which is actually on the last slide, and here it's represented over here. This is still just a linear combination of this, because it's linear to linear. Linear just means rotations, okay? What happens when we move to the nonlinear methods? Well, a nonlinear principal components regression, there's a nonlinear step in here. Certainly, remember in the last slide we had T1, T2, T3. This is just the architecture slide. You have as many of these T's as you need. All right? You generally, with the nonlinear biased regression methods, you'll use fewer of these values. And these are, again, linear. Here's your original measured data. You get this from a linear combination. Then this one you get from another linear combination. But these two are orthogonal related to one another. Okay? But then you put in a z step. Then you calculate this, and then you put a nonlinear function. So you run these things through a nonlinear function, such as, what the heck does this say? You'd use T1 and T2, but for nonlinear PCR or so, you might use T1 squared, T2 squared, and T1 times T2. You see what I mean? So now there's a nonlinear step in this architectural flow to get your measured, the thing that you're trying to predict. Got it? So when you're all done here, this is not a linear combination of your original variables anymore, because you put a little nonlinear function in this architectural flow. Got it? I hope this is helpful. It's sort of like, how's the data flowing through? Well, let's look at a more complex architecture. Neural networks, for example, and this is one type of neural network. Here we start out with the measured data again, and we want to make a prediction. And in here is all the model stuff, right? Again, we have two layers, just like in the PLS or so. We have two layers, or 3 layers, excuse me. They're called layers of these nets. Here's your original layer out here. Your original data comes in. Then there's an intermediate layer here, then another one before you make your prediction. Now, there is no neural network, okay? There's all kinds of them. Everybody's playing around with all kinds of things, but there is a type of architecture, and in fact there could even be more hidden. This right here is called a hidden layer of nodes. Okay, now you'll notice how similar these things were to our surrogate variables before. All right, well, let's look at the first difference. Certainly these guys are at first formed from linear combinations of your original variables, but then those values go through a nonlinear function here, which we have a couple of them that are often used on the next slide. So right away they get nonlinearized. Okay. Then, after these numbers, these are like the surrogate variables, they're transformed to nonlinear functions already. Then they're combined again in another nonlinear way to a value over here, and that again can be subject to another nonlinear transformation, and then that gives you this value over here. So look at what you have to solve for in the model. You have to solve for all of these linear combinations of coefficients. So if you've got 1,000 variables here, you've got 1,000, 2,000, 3,000 unknowns to calc. That's the linear weights. Then you have nonlinearities in the functions. There's parameters in this nonlinear function that you have to solve for. That's another half a dozen or so. Then you've got the next nonlinear set of weights to find, and then you have the parameters in this nonlinear function. So in many cases, you have to be careful you don't, what they call, over-parameterize the system, because this model will fit anything, including all of the noise. It'll fit it perfectly. You can get perfect fits of anything if you include the right types of nonlinear functions and enough of these nodes in this hidden layer, it'll fit anything. All right, so in that sense, if it fits anything, can't you think of it as sort of a library search? A library search, you ask a question, You go into the library and you get your answer back. If the answer is explicitly in there, you get it back exactly. Very similar here. Sometimes these neural networks are called, they were originally set up to be like associated memory networks, not calibration models, but now people are starting to use them for calibration and modeling. Okay, on this? Now there's a lot of things to decide and a lot of parameters to get. What types of nonlinear functions you're going to use, how many hidden layers. You could use one hidden layer. You could put another set of hidden layers in here. How many nodes in the hidden layer, et cetera, et cetera. And this is under active investigation by a lot of people. The kinds of nonlinear functions that are commonly used are, one of them is called the squishing function. Now there are some unknown parameters that are in here, but I took them out, and I just have the basic function in here. It's like 1 over 1 plus e to the x, where x is the little value that comes out, goes into the nonlinear function, and here's the value that goes out into the next linear combination. You see what I mean? And this thing just squishes the data into -1 and +1. That's all, with the appropriate parameters. So normally there's a parameter here. Another one that's been used recently is, let's say, 1 plus the hyperbolic tangent of the value, or 1 over the hyperbolic tangent. And you say, well, which one's better? I don't know. They're just functions, you know. And I've spared you the conversation about how these things look like brain cells and all that. If you've ever heard any neural network talks, you always get the brain cell picture first, and I've just spared you from that. All of this research it's good stuff. What's most interesting to me about it are the architecture. The architectural flow gives you a lot more freedom than what we were working with before. Okay, but there's a lot more research has to be done here. Okay, and there's actually a journal called Neural Computation, and probably a few others. Where are we here now? Well, let me conclude at this point. You'll hear lots more about this, but multivariate calibration is getting heavy use in industry at the moment. I know CPAC sponsors. We just did a technology transfer survey, and the thing got transferred more than anything else was some of the chemometric stuff that we've done. So a lot of people are starting to think multivariate as opposed to univariate. That, to me, makes a lot of sense. I always say the world is multivariate. Arguments? Unfortunately, a lot of the world is nonlinear. Worse than that, it's dynamic. So you got to talk to the chemical engineers there, because we're not ready to handle dynamics yet. What dynamic means, as soon as you got this nonlinear model, it's changed. Oh, incidentally, we're going to talk about, changing models next. In just a second. Lots of field of application. Near infrared has been the big one, but lots of other things too. The area of calibration with nonlinear multivariate data is the subject of heavy active research at the moment. I don't think there's going to be a major shakeout for a few more years yet, but we'll see. And okay, that's really what I wanted to say there. I've got some references here that I can end up with. This talks about the theoretical modeling of PLS. Dave Halen's paper, and Dave's at Sandia, and in analytical chemistry is really a good paper on PLS and PCR. It's very readable, and it's got an excellent algorithm in there. Dave Ostin, I can flash this up a little later on if you wish. Dave Ostin published a paper on cross-validation. How's the best way to do cross-validation, I thought. And these are papers that we like very much. They have to do with what we call tensorial calibration, which is the way I teach the course now, but we don't have time to bring it in that context. Okay. And I believe, let's see, this one and these last two are CPAC tech reports before they went out as publications, and these two are, of course, are not. So references are stuff I can get that for you later on. Okay, Barry, can I go in? Good. Now what I want to do is shift gears and talk to you about a problem, and I think we'll have, is it 10 minutes to 10? Can I be a little over? Deb, is that okay? Okay, I'll go through this as quickly as possible. Young-Dong's going to talk about some of the latter stuff in this. This is multivariate, what we call multivariate instrument standardization. The paper is going to be published in the Journal of Analytical Chemistry in December. And the university has filed for a patent on this stuff as well. And Young-Dong Wang's the very, very bright student that I have who has done this work. He's a fourth-year graduate student from the People's Republic of China who married a very wonderful girl in the United States and will probably... Another brain drain, I'm afraid. And okay, he's going to probably stay in the United States. The idea is standardization. This has been, I got to tell you about this first. When I first heard of this problem, I heard about it from the people at Savannah River. And when I heard about it, they said, here's what happened. These guys were the first that I know of to put some of this multivariate stuff online. They took the Hewlett-Packard diode array UV visible instrument. They squeezed it, I think, down a little bit in the near infrared. No, this was invisible, UV visible. They developed the method online. They did all the fiber optic stuff and did everything that wasn't available at the time commercially to analyze uranium, plutonium, and I think nitric acid and a few other things online. This was really nice stuff. And then they called me up and they said, well, they want to make this a standard DOE method and start to send it around. But to do this, they had their nice calibration set at SRL, and then they told another installation to buy the same instrument, and then they would simply transfer the calibration model over there, and they could start analyzing, right? And they did this, and it wouldn't work. So I just said, well, it's not my problem, So I called up Barry Willis, who's the inventor of in Hewlett-Packard, the guy who he's going to be at the meeting today. He'll talk about the history of this thing. Don't ask them why they can't make the diodes perfectly the same, okay? It'd be very embarrassing. But at that time they couldn't. Maybe they can today. And there were subtle differences. And these multivariate methods are so precise that they expect you transfer that to another instrument, that better be the same instrument. I mean, same. And they're very intolerant of any changes, you see. So 2 years went by, and I kept on saying, well, I called Barry, and he said, well, we have this soup that we make, and we have this software that tries to make the same, but he didn't want to talk about that. And I said, that's a product. You should sell it. It's a great product. They didn't want to talk about that because it's just a nightmare. They were hoping it would go away. And it didn't go away and I just kept on saying, well, it's not my problem, It's not a problem with Chemometrics. Tell the instrument companies to make their instruments the same way each time. And then finally, I think it was Ernie Bachman that told me, well, Kowalski, if you don't solve this problem, then nobody's going to use this multivariate calibration, and all the work you've been doing is useless. So that got my interest real fast. It's the idea about the cooperation between university and industry. This whole thing came out of that cooperation, frankly. But it took the university 2 years to hear that there was something to do here. Well, it turned out to be a wonderful academic study, and we hope a practical one as well. The idea is you have two instruments, and you have a large set of data, a large calibration set, and you're going to calibrate this instrument with these methods that you're going to use, PLS or whatever. Okay? Now, what you'd like to do, and see this data, this is supposed to be all of the spectra on your large calibration set. What you'd like to do is, what you don't want to do is take all of this calibration set over to this instrument. And there's a lot of I'd give you a lot of examples why that's true. Although that would be the best thing, correct? You would think you can't do any better than that. Is that right? Wrong. Young Dong will talk about a case where you can do better than that using standardization. But I won't steal his thunder. I'll let him talk about that. All right, back here, you don't want to calibrate this instrument. So what you'd like to do is transfer the calibration from model and continue. Well, that's problematic, as I just described to you. So what we thought is, well, you've got to get some information in common between the two instruments, because if you don't know what the difference is, it seems to us you're dead. We haven't been able to solve it any other way. So we said we'll take a small subset of these samples, as few as possible, and measure them on both instruments. And from this subset, we'll build a mathematical correction somehow that will then allow you to analyze future samples on this instrument and use the calibration over here. Okay? Does that make sense? That's the reason for it. It's not that you can't bring the samples over. In some cases you can't, but you just don't want to. And we, in the publication, the earliest CPAC method, we actually came up with 3 different methods of standardization. Now, one is based on the classical calibration math. It's not classical calibration, but it's based on that math. The second was based on inverse. And the third one is direct. And it turns out that this method worked best, and we have since taken that to what we call piecewise direct standardization. And this is the only method that I'll talk about, because it actually works by far the best in the standard case of, let's say, near infrared or spectral data. Other kinds of things you may have to go back to direct. All right. The idea is, this is a matrix multiplication. This matrix, see, R1 is equal to, there's a picture of the matrix down below it, artist representation. R1 is equal to R2 times F. Now what we do is we measure a small subset of spectra on both instruments. Let's say three samples back and forth. Now we first thought they had to be subsets. So if you're analyzing corn, you'd take subsets of corn samples back and forth. If you were analyzing gasoline, it would be subsets of gasoline. Turns out I don't think that's true, as I'll show you. But all right, so you have the three spectra measured on, say, on instrument number 1. That's your standard. Then you have the same spectra measured, the same samples analyzed in the second instrument. Let's say you have 3 samples there. That's R2. So this matrix would be dimensioned 3 rows by lots of columns. Same here. Then what you want to calculate is another matrix F, such that when you multiply F times R1, you get R2. So it's just a matrix multiplication. So in the future, once you have F, you multiply F times any spectrum measured on the second instrument, and you get that spectrum as if it was measured on the first instrument. Got it? Now that's nice, because what do you use for a calibration model? You use the calibration that was built on the first instrument. And this has ramifications to standardizing, especially with what Young-Dong's going to talk about in his lecture Wednesday. Important ramifications that says you do all of your calibration in your central analytical lab with your big instrument, and you don't calibrate online instruments. You only standardize them. Okay, we'll get back to that. So what we have to do is calculate this matrix F. It's a huge matrix, and we were using these biased regression methods to do this until we figured out that most of the time the only data that's active is data near the main diagonal of this matrix, and the rest is usually 0 or close to 0. So that allows us to use very, very few samples and to be, okay, and I'm not going to go again through the detail of the math, I don't think. And that allows us to use very, very few samples to calculate this large matrix F, because it's a banded diagonal matrix, and we only need to calculate a few of those. All right, we've done lots of simulations to understand how the methods work. We find that piecewise direct standardization, it does work the best, and it works the best with the fewest standardization samples, because that was important. We want to use for what we now call transfer samples, the very fewest samples possible. Okay, and get the best data. We looked at, the first data we looked at was from Mobil Oil Company, and we looked at from Amoco, and I'll talk to you about that. And incidentally, all the software is available in MATLAB if you want to have any of the software, and Dave will talk to you about that later. So let me tell you about a couple of applications. Some near-IR transmission spectra from gasoline samples from Amoco, and I'll show you how it works in results. And then we'll talk about some data that we received from the Cargill company on near-IR reflectance of corn. And I won't talk, this is the data that Young-Dong's going to talk about, and this has a separate message to it, and this is really neat stuff, so I hope you can attend that. If you can't, come up to me afterwards and I'll tell you what the punchline is there. All right, now here's an example where we had near-IR transmission spectra of gasoline samples, 30 different samples, 5 analytes from 800 to 1600 nanometers. And here are the 30 spectra plotted one on top of one another. Now, the idea was to build a calibration model on one instrument and transfer it to the second one. You see what I mean? And then obviously correct this spectra in the second one. Well, if you take 3 samples out of the data set that are actually the ones that are the most unique, 3 samples, we have a method that does that too, the highest leverage samples, you see. They're not outliers. And you plot those 3 spectra, and they're offset on the scale here. Okay, these 3 spectra are offset here to show you. These are 3 samples from the 30, and you'll see that the 2 instruments, there's 6 spectra here. Class, I'm getting ahead of myself. So the 2 on instrument A and B are here, and then the spectra from here and here. You see, in these regions, they track pretty closely. But as you can see, here's the solid line here, and you see the dashed line is the other instrument. There's really significant differences. It's one thing that's amazed me is how different these spectra are. Incredible. So obviously, if you transfer the calibration model over to the other instrument, you get horrible results. In fact, I won't even show you those results. They're off the scale. They're so poor. After applying the piecewise direct standardization method, here we have solid line A, dashed line instrument B, and you can see they fall right on top of one another for the 3 different spectra. So what it does is it uses the subset samples to correct the instrument, the spectra measured on the second instrument to make them look as if they were measured on the first instrument. Okay, what do these samples have to do then? These what we now call transfer samples or standardization samples. They don't have to represent the space of gasoline or corn or whatever you're going to analyze it for. They only have to represent what I call the space of the difference between the two instruments, how these instruments differ. And they can differ by shifting of the wavelengths, not just the standard shifting, but very, very unusual rubber banding shifting, which means they can, they can not shift in this region, they can shift to the left over here, and they can shift to the right over here. Very strange. And also for linear and nonlinear intensity changes as well. So that's all we have to represent in the subset samples. All right. Now when we apply this, let me just say very quickly that the method works rather well. Here's instrument A. These are the errors you get. Here's your standard error of prediction that I described to you. And here's how well you do where each of these, there's 5 different analytes, A, B, C, D, E. They were like aromatics and a few things like this, but Amico wouldn't let us assign a name to the analytes, so we had to use A, B, C, and D. So there's 5 different calibration models. If you take all the samples and calibrate instrument A, you get these errors. You can see they're pretty small. If you take all of the samples and calibrate instrument B, you can see that's about as well as you can do. Instrument A and B are similar quality instruments here, so their results are about the same. And if you do standardization, you get slightly worse results, which you expect because you're only working off 3 samples. If you want to take 4 subset samples or 5 or 6, these errors come down pretty dramatically. But the minimum number you could use is 3, and that's what these results are. And if you say, well, what if I just take those 3 samples and recalibrate with only 3 samples? Instead of standardize, I'll just recalibrate, but use only 3 samples? No, you can't do that. It doesn't work very well. So you obviously gain a big advantage by using the calibration method built on a good instrument with the full set. Get what I'm saying? So standardization is your next best alternative. When the instruments are similar quality, the best thing to do is recalibrate with the full set, but you can do quite well by a carefully chosen subsets of samples. So it works well even with 3 subset samples, or what we call transfer or standardization samples. The spectra are very well matched, and the standard error prediction from using piecewise direct standardization is usually on par with, or up to at worst, let's say about 2 times poorer than the full set cross-validation, which means the full recalibration. Okay, that's just some quick results. Let me switch over to another data set where we had 3 different instruments to standardize. I won't talk about all of them. We had 4 different analytes we were interested in building models for. So we built 4 separate models for moisture and protein and things like this. And they're corn samples. Now here's the wavelength regions, a little over a micron to about 2.5 microns. And here are all the spectra if you plot them for all 80 corn samples. If you take, let's see. Now, the nice thing, here's the 3 subset samples that were the most unusual corn sample spectra in the set, which means they had the highest leverage value. And we would therefore, if we're going to only use 3, we would use these 3 samples to transfer from one to another. But Cargill did us a major favor when they did this data analysis. They were clever enough to, every time they ran these spectra, they also ran the spectra of polystyrene, nothing to do with corn, and a NIST standard, which I believe is a rare earth oxide standard in glass. Now, unfortunately, they didn't do one more, but, they didn't do this for us. They did it for them. And they were kind enough to give us the data. So this was a way for us to consider, well, do we have to use always subset samples in the analysis, or is it possible to get even reasonable results with what we call generic standards? And some work that's been done shows us that, obviously, to jump ahead, generic standards work very, very well. And I'll show you what we're doing here. So in this particular case, we have 3 different instruments. So that was one study. How do you do from transfer A to B to C and all that stuff? The other one was we have 4 different analytes. The next one is we had different day-to-day variation. I'll only talk to you about a little bit of the results. But the most important thing in this data set, for mine to explain it to you, is we can try our standardization using 3 subset samples, or we can try 3 other samples. We don't have 3 generic ones, so we'll take 2 generic samples and 1 of the subset samples. Okay, it's as close as we can get to, because with 2 samples it just doesn't work at all. We need 3. And there's a reason for that. Well, jumping ahead, here's the error analysis. And let's look at percent moisture in this particular case. There's oil, protein, and starch. But in the moisture analysis, here's subset standardization. Here's no standardization. The errors are poor. And here's the best you can do with just 2 of the instruments called R5 and R6. Okay? And when you do piecewise direct standardization, you see, here's your error bar right over here, which is very comparable to the whole calibration set. You see? Here's your error. You want this to be low, these error bars to be low. That's your standard error prediction. So it says, if you use the subset, 3 corn samples, to standardize, you're using the calibration set on the instrument number one. You're measuring the unknowns on instrument number 2, standardizing their spectra to look like they were measured on number 1, and then using the calibration model on number 1. You get very, very comparable results to completely recalibrating the other instrument. That's good. But the interesting point here is look at the error bars, which are very, very close and not statistically different if you use generic standards. So you use the rarer standard, the NIST standard, and 1 of the corn samples, and you get essentially the same results. So that tells us that we want to go ahead and examine the generic standards, because it's not so much corn you're trying to represent here, it's the difference between the 2 instruments. Okay. Well, that was just some more results from transfer to 2 different instruments. So summarize, the direct standardization works better than no standardization or subset recalibration, much better. And it looks like generic standards may be possible to use in this. And we envision instruments in the future to have internal standardization such that when they're not analyzing, they're standardizing themselves. And they can standardize to anything you want. They can standardize to the corporate standards, to the corporate instrument, or to a NIST instrument, or to one in the Vatican, or whatever you want to do. And I think, indeed, in terms of some instrument development and things that I've seen going on in the instrument companies, this is definitely a direction. Now, later on, there's at least one more story. It turns out every time we think we're about done from an academic point of view on standardization, something else interesting pops up. But I'm going to let Youngdong Wang talk about that. And that is, let's say, can you do better than re-standardizing? And the answer is, looks like yes, depending upon the quality of the 2 instruments you're standardizing from. And there's some more to it, too. Any questions at this point about this? Yeah, that's it. God, we're done. Only 10 minutes late, but they didn't tell me we were going to take a break, so that's about it. So hopefully it'll give you some understanding of what's going on. As I said, it's not an easy subject. All my students are telling me this is not an easy subject, so it takes a lot of study and that. And Debbie, do you want to say something?
I'm done.
I'm done. Thank you very much. Yes?